After this long administrative introduction, let's jump straight to the core of our topic. What are embedded systems? Embedded systems are computers whose job is not primarily information processing, but rather is interacting with the physical processes. Think about it as simply, a computer, your laptop, you will simply crunch numbers, while an embedded system will be able to acquire data signal as well as actuate on the physical world, like controlling a DC motor, for instance, as it will be our mini project for the first part of this class. So they also bring a few non-standard attributes, which are the following. They are usually application specific. An embedded system is designed for a specific purpose. They are resource constrained. For instance, you will not be able to implement, very often you will not be able to implement a complex Linux stack on the system, but you will have a very limited amount of memory you have to deal with. They have very often real-time, they have real-time constraints. The notion of real-time, we will cover that amply in this class, but it's definitely not something related to quick, immediate. It is something that is simply bounded in time. The notion of real-time means that you are able to perform a task before a given deadline, and this is something predictable. The software must run forever. Definitely you don't want your pacemaker to get a blue screen. You want this pacemaker to work all the time, so your software must run forever. And finally, there are more and more recent attributes that are coming with embedded systems, such as networked operations. If you create sensor networks, for example, they have integration with physical processes. They are performing a specific task you want to act on the existing world, for instance. And this is why a broader view is now to consider a cyber-physical system. Cyber meaning something that belongs to the computer world, physical, something that belongs just the physical and the way we interact with the world. And the cyber-physical system makes both of them connect together. Why should we care about embedded system? That's a very fundamental question, and this is a very easy answer. Only to pass this class? Well, definitely not, right? Simply because they are absolutely everywhere. Everywhere from your smart clothes, your car, your smartwatch, your smartphones, and so on and so forth. In addition to that, we are also transitioning to the Internet of Things, where more and more objects are connected to the internet, are communicating. That plot is actually pretty outdated now, but it shows a very interesting set of results. This is the growth of the mobile phone market in the US. It has been the most successful technology ever so far, and it is definitely not going to stop now that we're moving not only to that smartphones, but smart object, smart dust, and so on and so forth. We must keep up with the future. This is going to be everywhere. There has been this transition, this inflection point between desktop computers and mobile computers. Already back in 2014, the number of mobile system overgrown the desktop users, and it's continuing more and more with the Internet of Things. Think about it, 2014 was only about smartphones. Now we have Amazon Alexa, Google, whatever voice-operated assistants all over the place in our homes, and so on and so forth. So this is something that keeps going up. So what's important to do is also to make a very strong distinction between embedded systems and general computing. I already mentioned a couple of attributes. Let me emphasize on a few more. Time matters in embedded system. As fast as possible is not always good enough. A computer is doing things as fast as possible. But you can imagine very simply that if your airbag is simply deploying as fast as possible, but right after your nose already crashed in front of the steering wheel, that's definitely not good enough, and you need to be able to control that. Concurrency must be intrinsic. In a regular computer, concurrency is an illusion. It's time sharing on your processor cores. Now, of course, people will argue that we have multi-core system nowadays, but you still have this synchronization point and everything gets concurrent at some point. With embedded systems, we have a real level of parallelism where we will be able to react to outside interrupts, outside information that tells you you have to stop, you must react on something very particular. Processor requirements can also be specialized in embedded systems. You will have systems that will apply machine learning at the edge, and you will be able to grind a lot of number very efficiently. So you will have specialized operators, specialized instruction, and so on and so forth. And that also makes a strong distinction versus general computing. Finally, we have programs that need to run essentially forever, programs that should not end up with a memory usage that is bounded, that is not bounded, so you cannot tolerate leaks. Rebooting is not acceptable. Think about it. How would you reboot a Mars rover, for instance? At the same time, you definitely don't want to just explode totally your memory size and get locked very quickly. So that will introduce some very specific software programming techniques where we will not make a lot of use of dynamic memory allocation. We will control our memory at a much lower level and really understand what we do. Since the early 2000s, there has been this embedded systems convergence. Before the year 2000, embedded system was only about making cheap devices, cheap and specialized devices. Very cheap cameras, cheap entertainment system, cheap communication, cell phones, and so on and so forth. But since late 2000, everything tend to converge into the best example of all, which is a smartphone, but as well as many other devices. So the new reality for embedded systems is that in the end, embedded systems are not really specialized systems, they are ultralight computers. They are computers that can do a lot of things with a very low cost, very limited power budget as well. Also, an important concept is the notion of system-level co-design. When you build an embedded system, it is not a matter of software, it is not a matter of hardware, it's a matter of both. The interaction between software and hardware. And you need to know which part you'll be able to do in software, which part you will be able to do in hardware. This is why it's also so important to consider modeling of our system right during our design phase. So why study the ARM Cortex-M architecture that we are focusing on in this class? I'm showing you here a plot that shows you the amount of tablets sold per year that contain an ARM processor compared to an x86. So the conclusion is that clearly ARM is leading the way in this market. And similarly on this picture, it shows you also the revenues for microcontrollers between small microcontrollers, 4 and 8 bits, 16 bit, and then 32 bits. As you can see, this is an ever-growing growth, and the bottom line is that the Cortex M0 is one of the most important representative processor of this trend. And this is what we will focus on in this class.